Ramsey Library Video Production is proud to present a Fall 2019 Brown Bag Talk. 2 real-world physics applications, road mirages and eyeglasses for myopia, by Dr. Michael Ruiz.
All right, got a very small seminar here, group. Well, welcome. I'm glad to be here to give a talk on 2 papers that I've recently written. I am Michael Ruiz, Department of Physics and Astronomy, and we're going to talk about 2 real-world physics applications, the road mirage and eyeglasses for myopia. These are the 2 papers that are being published in the November issue of Physics Education. So they'll be coming out next month. In the print version, they put the internet version up early, so I was able to get the papers or abstracts and the PDF files. And one is on road mirage angle, and the other is on diopters for a myopic eye. I worked on this during the summer. It takes a while for referees to look at the paper and then we make the revisions, and by the time it gets to the stage of publishing, it could be 2 or 3 months. All right. So mirage is first. Mirage. Now this was a personal story for me because when I was a boy, I saw the mirage in a trip the family was making to North Carolina. And I made the trip to the same place this summer. All right, so the trip to North Carolina was when I was 10 years old. It was 1961, all right? And I saw this water, what appeared to be water, in the road. See, look at that, that's the mirage. And there's like no water there. Isn't that awesome? Looks like a reflection. And the brain interprets that as water. And we're gonna explain how that works today. So, my dad had the movie camera. Now, I have some footage of the road, but not the mirage. We didn't happen to have the camera rolling when I saw the mirage. But it was on this trip from New Jersey, Camden, New Jersey, to Beaufort, North Carolina. All right? So here's 1-minute clip of the video of the trip. My dad had a camera that just did the movies. You know, you cranked it up. 1.5 minutes, turned the other way around, another 1.5 minutes. So, heading to North Carolina. I see the clouds there, and the temperature's not quite, the road has to be pretty hot for this to happen. So we're not getting that there. Welcome to Beaufort, North Carolina. And there's my dad, see? And this is when I first found out about the mirage. That's me and the gold shirt. That's the Inlet Inn in Beaufort, North Carolina. And there we are, that's me by the sign, Inlet Inn. And that's me this summer. I had to go back there. They moved the sign, and the building structure is a new one. But we stayed at the Inlet Inn. My wife and I stayed at the same namesake, inn back there. So why does water appear in the road and then disappear? Remember my dad saying, son, that is a mirage. And then my interest in science increased, and that helped push me toward being a scientist. And we're going to explain the mirage today. So let's look at a gallery of pictures I took during this trip. And let's look at some mirages. Now here you can see far up ahead, looks like there's water in the road. So we're getting the effect here. And that's a little more pronounced. Now when you get very close, it's gonna be in front of you. Like you never can catch it. So the famous desert mirage, where the sand is hot and you see the water and you're like struggling, you're dying of thirst. You see the mirage, but then when you keep going toward it, it keeps receding. It keeps farther and farther away. You never get there, all right? So nice to have a car or a vehicle to see a reflection. It looks like a reflection, but technically it's not. I'll explain it. And those signs captured my imagination, the signs, the orange signs. So we're going back to Beaufort, North Carolina, my first return visit after 1961, like this summer. Like, that's like almost what, like 60 years, right? All right. And then I'm seeing these mirages. They're very strong. The day we're traveling is like June 1. It's a very strong effect. And those signs capture my interest because then I get the idea, I'm supposed to be on vacation, I understand that, but I get the idea that if I could watch when that sign just disappears, that would be at the angle, and then time the seconds for the car to reach the sign, I would know the distance, I could do a little geometry and measure the angle in a car. I said, this is a good thing to write up if it works. So that was the idea. The orange signs gave me the idea, since there are lots of them all over the place on the highway. So here we go, getting a little closer, but still the effect is there. Some of these I did zoom in. I had a picture zoomed in a little bit more, either with the camera or later, zoomed in later. Now there's that water. Just fascinating to see that. Look at that nice orange reflection from the sign. And I looked at the other lane. Look at that, the cars. See, it looks like a reflection. It looks like there's water in the other lane on the other side. And here, I love those lights. See, that's coming from this vehicle here. It looks like it bounced off the road, all right? The lights, all right? And here, look at over here, see? All this is mirage underneath there. And here, the sky, see, the sky can be the mirage. It doesn't have to be a sign. It could just be the blue sky or the clouds. And there's no water that day, like there's like no water on the road, right? Because you look at that picture, you may say, no, that's got to be moisture there. No. And this is the sign that I'm going to focus on in the experiment. All right. I need to know the size of that sign. That's going to help in the analysis. There you go. Goldsboro ahead. Kingston. Right. Kinston. Look at the yellow. Isn't that neat? See the color in the mirage. And there we're getting this structure here. And I like this one. This is a road that's dipping down. And the secret here is the road has to be hot. So the road's hot, and the light, and I'll show you how the light will bend so that this effect takes place. And this next one looks like you just get the wheels. Just the wheels of the vehicle, because the road's like taking a bend down. This one shows looks like there's a lot of water there, but there's not. That's all mirage. And here, like the white building there, you see that white there? And I want to show you a car that's about, this car is a car that's going to come in right to the road. So we see this mirage, these two cars, and as this car comes in, I think that's a police car. Check out that, like a splattering of white in the road, all mirage. Isn't that nice? Look at that. See? All right, so let's try to analyze what's going on here. And this is going to be part of the paper where we analyze this. I went to the website, and you might recognize Bud. You see that tuba player? That's my former office assistant. That's Bud. And it's Bud Holmes. Yeah, Bud. There's Bud. So, like, we wrote a paper a few years ago, and the editors were so impressed by the tuba, they made it their icon for their website. If you go there now, that's been up there for like 2 years, and that's my living room. That's my fireplace behind there. And there's a paper I wrote with Bud, talking one day to the office assistant, and I was doing my sound classes. I had a student that blew a horn and got like 7 tones. He's just like, I can do 20. I said, what? 20? He said, yeah, by tuba. I said, I don't mean changing the vowels. I mean just blowing with the lips. Yeah, I can do 20. No. I says, no one knows this in physics. Are you sure you can do 20? He says, yeah, I can do 20. I know a guy could probably do 24. So we did a recording, and he did 24. He just played 24 notes. And these are harmonics in physics. We love this stuff. So obviously the editors thought it was real dramatic to have him there. So that's Bud, still up there on physics education. We're going to talk about the Road Mirage now. And I got to give credit to a librarian, because this journal was not at UNCA when I first came here. They had the physics teacher, but they did not have physics education. A physics education is published in England. So at that time, I talked to Robert Bland, who was a science representative, like he would look after the sciences. And I said, Robert, what do you think about, this is like a journal, it's overseas, and like, it may be hard to get this one. And it was a little hard, but to have these different like package deals and it could be expensive. So he did all this research, and he says, yeah, I can get it. Because I was talking to him, I says, I can't really publish in a journal unless I read the articles and see what they're doing. Very important for me, so I really appreciate, the effort you put in there to get that. He says, yeah, I got it for you. So, and I was delighted, because that journal and I get along real well, obviously with seeing Bud's picture and all. Robert was here from 1983 to 2010. And there he is. And I wrote Robert an email. I says, Robert, thanks again for your help getting physics education. I have kept my promise to publish a paper in that journal within a year. I made that deal with him, and he's real polite. He writes back, great, I wasn't really going to hold you to that, I'm glad the journal is of use to you and your colleagues. So a very, very important journal for me. So important that I stopped publishing in the American Journal, because they were so fast, and the reviewers, we just get along, and just like it was a good match. It was a good match. So I have 2 papers coming out in November, all right, the 2 that we're talking about today. So here's how the waves bend when there's different temperatures, and I'm going to use sound as an example, since it's a nice waves, something true with waves applies to light and sound. So here we'll use sound. If you have a lake, the lake is cool, the hot air rises, and if a wave, if you say something or sing or whatever, then this is a crest of a wave. Think of it like if you were to drop a stone in water, you would get these circles, waves coming out if you kept dipping your hand in there. So these circles come out, like this is a circle, like a wave in the air, all right, for a sound. And since the here it's cooler down there and the hot air rises, the sound travels faster above. So the top of the wave crest is getting ahead of itself, see, ahead of the others. And the effect is it curves back down. So we say like the sound carries at night. Say it goes, you can hear someone across the lake where you may not even hear them in the middle of the lake, all right? So here's a few seconds from my sound class demonstrating this for you. A cool lake, if you have a cool lake and you have a hot air rises, so it gets hotter. When the sound is traveling like this, the top here, the waves go faster and they get ahead of themselves. And because the waves go faster, the effect is the sound carries at night over a lake. They use the term like sound carries. That's more of a colloquial expression. It's really the refraction. And they call that a temperature inversion, because in the daytime, it's hot down on your asphalt. Now, the road in the daytime is going to be the hot thing. So when there's a lake and the hot air rises, meteorologists call that a temperature inversion, because usually it's going to be, during the day, the asphalt's going to be real hot. Like if you walk barefoot in your driveway, you get burnt, all right? So that's the case for the Mirage. It's going to be hot there. So, but the light does a similar thing than the sound does. This cup's hugging the cold. You see how the cold, hugging the cold? So if the cold is above, then it'll bend like this. So it's hugging the cold, and that's going to get us like the reflection in the road. All right. Looks like a reflection. So this is what you have. See, it bends, hugging the cold. For the light, the cold was down below, so the arc was the opposite way. So here's the sign. The light will come, and just like the light traveling faster in the hot air will give the curvature, come up here, and this is called the mirage angle. That's the angle that is defined by seeing the very bottom of that sign, and then if you get closer, you lose it. You lose the sign. That's like the critical. That's the way you make the measurement. But then some other sign down the road starts to appear in the mirage, right? But you lose this sign. So does everyone see that? How that works? That's the key idea. That's the key idea of the paper. So you understand that. And here, what I've done is I've shown you that if I were at the same height as the sign, now a meter, that's almost 2 meters, 6 feet, like roughly 6 feet tall. Then what you would do is you would draw a straight line, and a straight line. This is the middle of the road. I'm going to time when I lose the sign, the visibility of the sign. I'm going to time how many seconds it takes me to get to the sign, and that's going to be 16 seconds in the car. Car's going 70 miles per hour, which translates to 30 meters per second. A meter is about a yard, all right? And the physicists love to use meters. So meters per second times the 16 gets you, 3 times 16 is 48. There's a 0 hanging around from the 30. So it's 480 meters, 480 yards, all right? So that's pretty far, but if you're going 70 miles an hour, you get there pretty fast. So if you look at the midpoint, you would divide that in half, 240 and 240. And this is not drawing the scale, because if that's 240 meters, 1 meter is like a real small little bump, all right? So this reminds the reader in the paper, I include very much not to scale, all right? Then you can get this angle from this height compared to this 240. In the old days, there'd be tables we would look up. Now we have a calculator. It's called the arctangent. We would plug in 1.8, divide it by 240, press the button, and bingo, out comes the angle. And this it's less than 0.5 degrees. Now, 90 degrees is like this, 45 degrees is like the peace sign, and if that's 40, then 1 degree is like a real small slice, and then if you go a half of that, that's really a small angle. So a very, very small angle. All right, it's time for the experiment. This is what happened. I was driving the car. My wife's driving. I'm in the passenger seat. My wife's driving, and I'm going to go for it. I see the sign, and I'm going to wait until the sign vanishes, and then I'm going to time how many seconds does it get to the sign. I'm going to figure out like how far the sign is away from that vanishing point where I'm going to get my angle. So wife's driving at 70 miles per hour and held it pretty steady. If not, I go for the next sign, and I warn the readers. I says, look, if a student's doing this with their parent or whatever, don't mess with the driver. If they have to slow down, just wait, go to the next sign. Safety issues. There's plenty of signs. Take your time. All right, so here we go. We'll have a few more details for the physics teacher, which we don't need to worry about for the essential idea of the paper.
This video is about the road mirage. Note the 2 orange signs ahead. The car is maintaining a fairly constant speed of about 30 meters per second. The mirage of an orange sign on the left will be shortly visible. There it is. It appears that the orange is reflected from the road off a layer of water. We are going to note when the mirage of the orange sign vanishes. Now, every second we travel 30 meters. We are getting close to the sign, almost there. And as we pass the sign, we will note the distance, 480 meters. We will need the dimensions of the sign for our analysis. The low soft shoulder sign has the standard dimension of 3 feet for each side, that is 0.9 1.91 meter. Therefore, the vertical diagonal is 1.3 meters. By measuring the pixel lengths with a software graphics program and using length ratios, we arrive at 1.8 meters for the length of the support for the sign. Next, we will need the height from the ground of the observer in the car.
When I took the video of the Mirage, I had my smartphone at about this height from the ground. Getting to 2 meter stick, 120 centimeters, 1.2 meters.
Though refraction is the cause of the mirage, we will approximate the mirage as occurring from one single reflection from the road surface. We pick the lower part of the sign as the last rays from the orange sign reaching the eye. Taking the ratio of 1.8 meters to the sum of 1.2 plus 1.8, we arrive at the 288 meters from the sign to the point of reflection. The angle alpha is the mirage angle. The tangent of alpha is 1.8 over 288. When you use a calculator to obtain the arctangent, you find that the alpha angle equals 0.36 degrees, a very, very small angle. Introducing refraction, the light bends away from the normal as it enters a medium with less index of refraction. The index of refraction of air reduces as the air gets warmer. Note that n times sine of theta is a constant. For the mirage, we have a gradient in the index of refraction. We have a cold temperature at the observer, the temperature from the weather station, and a hot temperature at the road surface, which value we find from engineers who study asphalt surface temperatures given the ambient weather temperature. Then the refractive index of air can be calculated in each case based on the temperature. Plugging in the values, you can solve for the angle theta and then find its complementary angle alpha. The calculated value is essentially the same as that found earlier. I would like to thank my dad for telling me about mirages when I was a boy on a family trip to Beaufort, North Carolina in 1961. Returning 58 years later, I shot the Mirage video. Also thanks to John Rideout, transportation coordinator at my school, for discussions on highway lane widths and signs. Finally, thanks to my lovely wife Margaret for driving the car for the video.
John played an essential role because I didn't know the exact size of the sign, and you can't really measure it. It's a little too high, and you don't want to be messing around on the road anyway. And then I remember being on the transportation committee for 4 years, being chair about 3 years, and John knows all about transportation cars and stuff. So, like, he knew. He said, like 3 feet. Like that's for that road, that'd be 3 feet. So I said, wow, that's awesome. I really needed that information, you know. And then he gave me some references. You know, the different size roads would have different size signs. And he says, for that one, that highway is 3 feet. That's very, very important. So John came in handy. He also helped me out with the lane, how wide the lanes are. He knew all the roads, like the rules, transportation guidelines. So he was a great resource at UNCA. So you got Robert Bland and got now the transportation coordinator helping me out here. It's a great community at UNCA. So safety issues, there's several. We're going to talk about, we need to have the temperature. Need to have the temperature of the air and the temperature of the road, the air near the road surface. And we don't want students getting out of the car with these devices that you have that you can like point to the asphalt and get a reading or something. No. I found references engineers had made many measurements and averages over the world, you know, for different latitudes. This is safe that we consult the books there rather than try to get in do an experiment in the highway when cars are going like 70 miles an hour. We don't want to even do that. And I also mentioned that when I bought one of those things on my asphalt driveway, I got different measurements anyway from different places. So the engineers, when they do a lot of measurements and do an average, you're better off with that. So that was another safety issue. Don't get out of the car, try to measure a sign. Don't get out of the car, try to measure temperature. Rely on the references. So this is just a rough idea with the map to show you where Beaufort is. Beaufort, North Carolina is on the coast there. This near Morehead City. Morehead City is about like a mile or so from Beaufort. And we were at New Bern, when we were doing this video. I was at New Bern, North Carolina, Beaufort. Yeah, my dad was stationed in World War II in Beaufort, and he became very friendly with a family there. And the father of the house had some kids and said, "Son, like, you're welcome to stay here. You have a place to stay." He said, "Well, you can stay with us and a family, since you with the Coast Guard, close by." And so my dad stayed 4 years and became very close. And I was visiting the last survivor of the family. She's in her 80s, Nita Moore. So it was a very personal visit tied in with the research. All right. So here, temperatures at New Bern. Now I have Chris Hennon, our atmospheric sciences department, digs this up for me, because I wanted to know the time of day. A nice thing about the videos you take or photos, it tells you the time. So I can say exactly, I took the video 3 o'clock and 34 minutes in the afternoon, and what was the time at the New Bern station, which would be real close, say. And he helped me get the temperatures, because you want to know the temperature of the air above the road, where I am, and then the temperature at the road, the air right near the road, okay? And the reviewer was fussing with me a little bit on this, like, how do you know if there's not a heat sink there or something? So, we had that explained. It's a rural area. It's not like New York City or something. So the temperature be very reliable at New Bern. And that was, experience of dealing with referees. They always bring up good questions, and you have to, they get you thinking about things. So the bad news is my wife's car has a temperature sensor, and it was right there. And because I drive a Toyota that's from 1994 or something, I don't have one. I never thought to look. What misfortune, right? Because the temperature was right there. And then when I had the camera, I went over to the speedometer. I had just missed it in the video. I was hoping I might catch it in the video. So that caused a lot of grief, but then don't give up. This is like real life, right? Real life science. Sometimes an opportunity is missed. You have to get the answer another way. So with the airport, the time, all the data that Chris Hennon has access to with his meteorology, tap into the climatic data center, and he got all this stuff. So he helped me get it, but I wish I had read the temperature on the car, which is right there in front of me, all right? Now, this helped appease the reviewer. I says, look, New Bern sensor station's only like a few kilometers, like a couple miles. I says, look, I'm gonna go to Raleigh now if you wanna worry about a heat sink. Now, I was very polite how I explained this. I said, I'll go to Raleigh, where it's the worst case scenario, Raleigh area. And I says, and this is area is what, hundreds of miles, right? It's a big distance, right? To go from Winston-Salem to Raleigh and beyond, there's a lot of kilometers there. And I said, look at the temperatures on a hot day. They'll hardly vary. It's about the mid-state, all right? 82, 83, 81. And we're using Celsius, which is half, a degree of Fahrenheit is half a degree like in Celsius. And I was picking uncertainty plus or minus 1 anyway. Even if I used the wife's car reading, I would have still said plus or minus 1. And I'm well within plus or minus 1 for like major part of North Carolina, where we have cities that would maybe affect the heat or something. What the reviewer was worried about, heat sinks, right? So that was fine. They liked that. They said, and I was shocked it was that uniform. And I kept checking it every day for about a week when I was writing the paper. I said, man, it's still like this, even at night. What is this? What is this? Now, in the winter, I think it's not so. But when the temperature's like warm and it's hot, boy, it's like the same everywhere. Now, the engineers telling me what the temperature is near the surface, the asphalt temperature. So I found this work by engineers where they said, here's your latitude, UNCA, North Carolina, we're all about 35. It's close to 35 in north latitude. And this is the air temperature. And luckily, with maximum air temperature that day was about 3 o'clock. So it was at the maximum air temperature, like 27 Celsius or something, like 82 degrees. So I find that 27 Celsius, it's about 82 degrees. You got the Fahrenheit there in parentheses. And then you go find where it intersects your latitude. And that's the temperature of the road, 127 degrees Fahrenheit. Say, isn't that neat? So that's what I recommend all the teachers and students to do. Check this chart rather than trying to measure stuff, which varies anyway. And they have this for the entire world, pretty much, with the latitudes, or a lot of the world. And it was wonderful. They did such a great job because I knew that the reviewers would fuss at me. They went, "What's the uncertainty?" And they said they're within 3 degrees Celsius or something like 85% of the time. Perfect. So I could then say plus or minus, and they want to know that. When you have a result, what's the plus or minus, how close are you? So when we did all this analysis with the formula, I get the 0.36 plus or minus, I'm close, I'm right there, and that was a delightful experience when I found it was going to work. I said, this is amazing. I'm actually getting the 0.3, 5, 3, 6, using formulas with index of refraction and other stuff there. But one referee, the first referee I had requested. This guy's brilliant. I really respect him. And he gave me 12 things to analyze, improve upon. I did it all, and then when I sent it back, the second referee says, sorry to hear about the first referee being ill, can't respond. I'm going to take over. He says, I'm happy with everything you got except one thing. I said, one thing? What's it now? He said the temperature of the road was this 127 Fahrenheit. But what about the air right above you're using the air right above there. How do you know it's the same? I says, well, equilibrium, no current, no wind, equilibrium. I had said something like that, but that wasn't enough. I mean, he's confused. So I'm taking out my garbage, and Chuck Bennett's down there, because he's my neighbor. I says, Chuck, what's with this road surface? Why can't I say that the air real close to the road's the same thing, no wind? And Chuck says, oh, wow, there's radiation, there's this, and so I'm in big trouble already, because he's now going off on tangents and all. I says, no way I can use a theoretical argument and convince the reviewer. If Chuck and I can't come up with it, he's my friend, all right? So I says, okay, we're gonna have to go engineering. There's always a solution, you don't give up. I found an engineer that measured the road surface and the air right above it, and did a few measurements. I said, it's perfect, and the grass matched. It was perfect. So I says, hey, look, this, no problem. They just backed off and said, fine, publish it. All right, isn't that cool? Engineers come through. When you can't figure out the theory, because it's complicated, there's the radiation from the sun, maybe some gentle currents, all right, and all this stuff, that you rely on the engineers. So they just measure it. And there was 2 papers that had measured that. Beautiful. So that saved me. Not the first time engineers saved me. They saved me before. And it's fun. You have to read other journals. And then Nancy's a star. She gets them for me, because we don't usually get engineering journals. I mean, this is not an engineering school. I mean, so I need all kinds of crazy papers. She gets them. All right. So my compliments for Nancy, interlibrary loan. So I get anything in about 3 or 4 days, and that's where these papers, came in handy to save the publication, all right? So glad you're here, Nancy. Another acknowledgement, all right, in the UNCA community played a role here. So there's results. The experiment would be my measurement in the car using the geometry that you saw, the triangles, 0.34 plus or minus 0.02, some uncertainty. In maybe a half a second off, then I'm going to be off by so many meters. I mean, it is exactly 16 seconds, could be 15.5. So when you put that in there, then there's a 0.02 degrees. And when you put in some uncertainty from the engineers saying we're not sure plus or minus so many Celsius for the road temperature, the main thing is that these overlap, that they're so close, you say, and the uncertainties, they're within, they agree. So that made my day when I discovered that, and I first thought it was going to work in the Inlet Inn when I was doing a rough calculation. I said, I can't leave physics alone, and I said, this is going to work. I was just elated, Then had to spend another 3 weeks doing the details and double checking everything. So that's it. Myopia is next. Myopia goes faster. This is simpler physics. But that other one plus this one, what is exciting to me is that when I showed you this thing with the trigonometry, the sine of theta or whatever, that weird stuff, I don't do that in my class with the general students because I teach art majors and music majors, and we don't do that. But the pre-med physics do it, and the engineers do it. So it's really in the introductory course that uses math. See, my class just uses, well, arithmetic. I use math, but just arithmetic. So you don't have any prerequisites to take my class. So I don't do that in my course. But for the journal, I wanted to, well, I had to, because a part of derivation required that. But the fact that it was an introductory physics course, the journal loves that, because that journal caters to intro type concepts. So for myopia, now the myopia, I'm watching this movie, Memento. What, Guy Pearce or something, this Guy Pearce, and it's a strange movie. The guy can't remember anything after 10 minutes. He's got to write everything down, here, and he does. So I'm watching this, and there's this scene where this looks just like this. So Guy Pearce is the lady here, and they have a shot through the glasses, and you can see the wall, the tattoos on the wall are real sharp through the glasses, and then they're blurry outside. So see, here's very, very blurry, and then here, see how that's sharp? So I'm watching this, and then they keep shooting it for 30 seconds. I go, oh, wait a minute. They must find this aesthetic, and it was very aesthetic. I said, I wonder if that was an accident. They were just shooting this thing, and they saw the tattoos, and they said, no, let's keep doing this. That looks interesting. And then they had a couple shots back and forth, and I thought, wait a minute, if that's the case, I can tell the prescription of the glasses. I can tell the prescription from just a picture. I said, I've never seen this written up anywhere, And then I would experiment, like when I was with Chuck Bennett, at a conference, I would look through his glasses and see things sharp, and I would have some fun with that. So I wanted to write this up, and I talked to my students. I said, I need some students to be part of this, because I can't, copyright. I can't use the movie. And if you try to ask Hollywood for permission, you never get an answer. They'll probably just ignore you. So I says, we got to set this up. So Merritt here, she volunteers her boyfriend, Danny, and he says, we'll do it. We'll do it. All right. We'll position ourselves so you can use our pictures in the paper. So that's what we did. Say from Memento. I came close. I almost got permission because Memento had a reference, and I wrote them. They wrote me back. They said, no, it's not us. It's them. And then they never wrote me back. But the first one did. That was amazing to get something back from movie folks, because. All right. So here's the idea. Now, Vlad, another student in my class, he helped me out significantly, and I acknowledge all these students, because I found with the iPhone, it is so good that I was having trouble getting the blurriness, because iPhone, nothing's blurry. It's the hole is so small, you don't need a lens. Like when you squint, you don't need your glasses, same thing. The pinhole camera effect. So Vlad says, no, what we do is we tap. We tap on the phone where her face is, and I'll focus on her, and this will get more what you want. I says, this is good, Vlad. A smartphone, you all know this stuff. They grow with this stuff. So help me out. See, in the movie, they got a real expensive camera. And if you have a professional camera, you can set the thing and get this very blurry on the wall and very sharp through the glasses. You can't do that as well with the smartphone camera because it's too good. It's made to be with different lighting, different situations to still look good. And here we don't want it to look good. We want to emphasize that. So if we had a camera and made the f-stop, the opening very, very large, then you need your glasses. Like at night when your pupil dilates, if you need glasses, you need them more now, see, because the blurriness. So we could really get a better picture. But I says, I can't do that because if I want to get this published, they're in love with smartphones. If you mention smartphones and you can do it with smartphones, all students have smartphones, they're going to go nuts. They're going to want it. If I say you have to have, a $400 camera or something that's manual control and all this, they're going to They're going to say, what's this? We're not professional photographers. Get lost. So Vlad helped me make it work. All right. So you can see it there. But in the movie, it's even more dramatic. Okay, so here's the deal. This is Vlad. See, we're taking pictures here. I'm holding this camera. He's holding the camera. I'm doing this. I'm showing you that the people far away look sharp. You see, that's the building back there. It's blurry. See how it's sharp there? So this helps understand if a person can't see far away, like it looks blurry to them. What you do is you use these glasses to make it smaller and bring it closer. And then, so they see this part of the Lipinski instead of that. That's blurry, but see how that's sharp? See? So this is the prescription for someone that has trouble seeing far away. This is called a diverging lens. It's not a magnifying glass is different. That's a converging lens that makes things bigger, and that's for folks that need to read a book, all right? This would be for someone that has trouble seeing a blackboard in class. Typically, the problem with younger students. As you get older, we all have trouble reading the book. So most of us who get older need to have the converging glasses, the positive curvature. This is called a negative curvature that makes things smaller, all right? And then if you have both, you have bifocals if you need to have something else like that. So this here brings the things that are far away to within 8 inches. And that's how you can prescribe the glasses. You could say, go up here, I do this in my class, student covers one eye, and go as far away as possible that you can still see it sharp, all right? And in some cases, it's 8 inches. So in other words, a student can't get farther than this, otherwise it's gonna be blurry. All right, and then here it looks sharp. So that's 8 inches, and that's 20 centimeters. And then the prescription's very easy. You just divide the 20 into 100, slap a minus sign on, that's it, -5 diopters. That's what the ophthalmologist does, or the optometrist does, that's it. And they find it by trial and error more, where they give you different, is this better or is this worse? Is this better or is this worse? And they're fine tuning, and that's the experimental way. Like the engineers measuring the road, that you can't beat that, all right? But this way is a crude way that does work pretty good. Someone takes off their glasses and go like this and say, all right, 20 centimeters you measure it in class, and then divide the 20 into 100, it's 5, -5 diopters. That's a fairly strong lens, -5 diopters. When I was a teenager, I had trouble reading the blackboard. But I was able to, if I did that experiment, I'd be able to get back, it'd be good until 2 meters, all right? Now 2 meters, like 6 feet. And then that was -0.5 diopters, because if you have 2 meters, is 100 divided by 200. And 0.5 diopters, that's a very, very gentle myopia. And then as I got older, I have trouble reading the book, and that's the opposite problem, and it canceled. I was like, Dr. Chandler, who went to UNCA or at Biltmore College back 50 years ago, or something, he was on Merriman. He says, yeah, it cancels because we're pushing. See, when you get older, you push out your focusing like this, and that's helping you see farther away. All right. I said, that is good. So it's like 2020, like in my 30s, it canceled out, right? In the 40s, I says, like, Doc, how long? He says, well, after 50, don't count on it. Like you know, and that's true. Now I need, you know, it's just pushed out so far I can't see close up. So isn't that neat? We got the -5. So what do we have to do here? We have to measure the distance from the glasses to her face. All right. See, the camera is focused on her face. If the camera is focused on her face and that image is sharp, that means we focused on the image through the glasses, like I did here. See how sharp that image is through the glasses, and everything in back there is blurry? So if I can estimate the distance from the glasses to the hand, I divide into 100 and put a minus sign on and finished. So I asked my students, says, why don't you come up here? I get students come up. I says, like stand like you're talking to someone like that. Like just stand, you know, close. And so like two students standing close together like this, you know, that's about like there, right? So I says, all right. I get another student says, you get the ruler. Let's measure that. Or anyone in class want to just estimate, you know, And it's like half a meter, say, half a meter, 50. That's what I usually get. I said, don't worry about exact. I mean, is it more like 25, 50, 75, 100, even 200? I mean, don't. So you're judging how close they are to each other. And if it's, half a meter, so it's like about 1.5 feet. So about 1.5 feet, see? So that's all you have to do. And when you do that, you got your answer. That's 50 centimeters into 100 minus 2 diopters, like we know. And it was, who was that other actor? Gaglione? Anyone? The other actor, it's slipping my mind. I mentioned the actors in the paper. Guy Pearce was the one that was farther back. And then his glasses is minus 2 diopters, like we got it, from just the picture. So that was a fun one. And then we went outside. We says, if we want to make this better for the iPhone camera, let's make the iPhone camera work harder. Let's pick the banner very, very far away, because see, indoors the wall is not as far away. We go real far away, this will be better. So we go out, of course, nothing better than have our library as the background and the beautiful banners of UNCA to have it published in an international journal, more visibility at UNCA. So here we have outside, and you can see now this be more blurry compared to the sharp focus, because now more drastic change in the distance. So we went ahead and did it outside. And I talked up the experiment. I said all the students have smartphones, and you could have students say we're going to find someone in class that has trouble seeing far away, and they'll have a prescription. So let's go ahead and put the eyeglasses, have that student stand with the glasses, have another student stand, and then you focus on where you get that image through the glasses as sharp as possible, all right? And then you take the picture and have someone, like someone there so we can gauge, estimate what it is, and then have other students in the class figure out like how far that is from the context, and then they could see how close they get with the prescription. Like the other one I showed you was very close. It was 8 inches. Of course, that was close, but you can imagine 2 people being that close and do the experiment and then estimate. All right, so that's good. And then we go outside. Now, Yanal here is in my class, and he wanted to have a cameo. I says, okay, but he says, you don't have to mention me. I don't have to sign anything. I'm just going to walk by like I'm an outsider. He says, I want to be in the movie. I says, you're in, Yanal, you're in. So he knows all these students, and he ran. I think he fell down and broke his arm or something, playing soccer or frisbee or something. I think on the quad. It was so he gets to walk by and looks over real cool. So he's part of the. So here we got Danny. Here's Merritt, and here's Vlad, who is very, very good at the camera, and the 3 of them got acknowledged in the paper. All right. So here's the video abstract. Goes with the paper. All right. Here we go. Hello. With the help of my students, we're going to show you that there are cases where you can tell the prescription of an eyeglass lens from just a photograph.
All right, Doc, say action.
Action.
My student Vlad is using his smartphone to photograph Merritt, who is facing him, and Danny, who is in the middle. But Vlad's challenge is to arrange for Merritt and the virtual image through Danny's eyeglass lens to be both in focus. The magic distance for the eyeglasses Danny has on is 50 centimeters. This photo shows the general idea. See the virtual image through each eyeglass lens. There is a left hand placed at the distance of the virtual images so that the hand and virtual images are both in focus. The distant objects outside the lenses are blurred. These glasses are strong, placing virtual images only 20 centimeters from the eyeglass lens. But we need a subject better than the hand so that the overall scene has enough clues for another student to estimate the distance from the eyeglass lenses to the subject. This distance will also be the same distance that the virtual images are from the lens. And from this estimate, we can arrive at the eyeglass prescription. The distance from the lens to the virtual images of distant objects is the focal length. The prescription in diopters is obtained by dividing the centimeters of this distance into 100 and including a minus sign since the lens is a diverging lens. Here's an example. We need to estimate the distance from the lens to the small virtual image of the letters from the distant wall. The key is to estimate the distance from the lens to the lady, since the camera is focused on her as well as the virtual image. This distance is about 50 centimeters. Think about how far you would be from someone having a nearby private conversation. The prescription for the eyeglasses is then -2 diopters. That's quite impressive, getting a prescription from just looking at a picture. But it's only possible because both the virtual image and the main subject happen to be at the same distance from the camera. We are outside here, and the distant object we're focusing on is a banner at my university. You can see in this detail of the photo that the letters are quite blurred when not seen through the lens. I would like to thank my students Merritt Tutwiler and Danny Secor for their roles in this demonstration, and also thanks to Vladislav Rakuski, the photographer and videographer.
What always fascinates me about the virtual image is that it makes the distant mountains tiny and close, but your brain interprets the tiny mountains as really big mountains far away. Like your brain doesn't say, no, wait a minute, there's a little mountain that I can touch. No, it's like the same angle that's going into the eye. The brain just interprets it that way. And it has to be far away, because that's going to be the focal length. When something's far away, it gets imaged. If you get closer and closer, you then lose the effect. But if the focal length of the lens, say, is something like 1.5 feet or 50 centimeters, then the distance to the wall is like over 10 times farther away. It's pretty far. Of course, the library is better. And when measurements are made for focal lengths, you really want a distant mountain or something, you know, for the effect. Better blur, since banner is far away. So we get the library in again. Look at that. The library it's published next month all over the place. UNCA library. So, well, that's the two papers. We got some questions here you want to ask about? That movie Memento, it was luck. I mean, because the distance of Guy Pearce was at the right distance where that image was, because it wouldn't work unless that coincidence was there. But it was there, and I believe they played up on that and let it roll, the camera, because it looked really cool. It was just very aesthetic. I don't think they would have planned it that way, the physics, you know. See, I needed to have the same kind of glasses, -2 diopters. And you know, eyeglasses are expensive. You spend hundreds of dollars. My wife recently bought new glasses, and so I go on the internet and I find these outfits, $10. This is $10. Like, what do you want? I says, -2 diopters, each one, $10. I'll get a -5 diopters in the paper. So I think I spent less than $50 and got like 3 pairs of glasses. I mean, they're not going to be really as good as the expensive ones you would get, like I say, the optometrist, but the lenses did the job. They were at the right focal length so that we could do the experiment. So I put that in the paper. It says you could, if everyone in your class, like, they don't wear glasses, you can still get some, all right, on the internet, you know, very cheap. Yes.
This is probably going to be a stupid question, but with the first experiment, when you were talking about the Mirage, I was trying to wrap my mind around how the increase in heat would affect. Does that affect the angles?
Yeah. The best way to do that is to go back to, let's see, this. Yeah, this kind of a diagram. So this is showing the curvature, and the curvature lets you know, like in this case, how far the sound would carry. All right, and in this case, this curvature, how much it would bend. So if it's a real dramatic effect, it would do more, and then you would be able to get closer. The angle would be bigger. You see, if it was gentle, it would be like smaller, and it depends on the weather conditions. But usually for this, all the angles are like less than 1 degree. They're like but they may vary 0.4, 0.3, or 0.6.
How would that affect the mirage? The hotter
Well,
the
how
temperature?
far is it away from you? Yeah, because the angle, when you do this, I go backwards to find out where if I have a tree, and the top of the tree came like this, that's the top of the tree down there. And if it was more like that, whoa, I get closer, like you had to be closer. Yeah, in other words, to get that, right, that's that mirage angle, is like where you have to be to get it. Depends on how it's bended, because see, if you get too close, then you lose it there, but then there's the sky farther down, or another sign or something, then gets it. So it's very, very interesting. A lot of diagrams in the books show this bending like a cup, or like a U, and no, and I explained in the paper, those diagrams are exaggerated, because if you put your hand out on the asphalt in your driveway, it feels the same temperature until you get like about a half an inch or something from the ground. So this thing really goes in a straight line, and it does that right down at the bottom. So it's pretty much, because one of the reviewers was asking about, well, these are the diagrams, so we had to go back and say no, it's, and I think I changed my original figure. I think my original figure had more of a curve everywhere, but this is more like until you get very close to the road, and then it's very, very dramatic. And the hotter the road surface, the more it will bend. And of course, what's complicated is that the light is coming from the sign, hitting the road, going to the road at all places. So you just happen to be catching one of those rays. But if you get too close, then it is not hot enough to make it curve enough, and then you lose it, you see. And then when I lost it, that's where I defined the alpha. That's the angle, and then we see how far we are away and do some geometry. But it's very, very subtle stuff, very detailed, and even though the physics physics is weird like that. People publish papers that get very hard, and the simple concepts there, but then if you go into detail and you want to know those engineers that measured those road temperatures, I mean, they had laser beams. I mean, it was really intricate stuff, to get some simple result. So the physics usually has a very easy. And when I work with my co-author, James Perkins, who recently got tenure, and thanks to the journal, we published, I think, 4 papers in that journal during his pre-tenure years. They're very fast turnaround. So that was good. I would say James, because I had the same problem, more so when I was younger, where you want to answer everything. I said, we'll never publish. If you want to know everything, we'll never publish. So we have to allow for some uncertainty and not knowing something. And because there's a point you have to let go. A point in the paper, you have to let go and say, I'm going to let the reviewers fuss with me. I fuss at myself enough, and they usually find something else. They'll fuss with you, and then you go back as part of the experience, say, how can we answer the questions that the reviewer is bringing up? So when you get the response back, it doesn't matter if they're going to be hard on you. It matters, you just don't want to see the word rejection, because if it says rejection, that means go home, we're rejecting your paper, it's not salvageable. So when you get the thing back and there's maybe a whole page of comments, you're looking for wait a minute, that's good. If it's a whole page of comments, they didn't reject me, they wanted me to elaborate on some things or talk about some things. And that's part of the fun. Then we get together and co-authors and we start to say, all right, how can we can answer this? I have one right now with James. We're doing on rockets. And I just got the reviewer comment back yesterday. This rocket thing's amazing. You go online and you find these, Elon Musk puts rockets in orbit, and they're amazing. They had the whole video and they had the telemetry. to tell you how high the rocket is and how fast it's going and what else. So we started doing analysis of the orbits from what the data they has. Today's data is everywhere, and submitted it, and just a few minor things to change. It was awesome. So we're going to fix that up this weekend and get that in. But yeah, these rocket things are amazing. They just show. And they land, like the stages land, like Space Shuttle would go in the ocean or something, go pick it up. No, these rockets, the boosters actually come back down, like science fiction. It's amazing. We couldn't believe all this stuff. Yeah, and that we were doing what's called a home in orbit, where what they do is they send the rocket up, and they're going like this, and then they do a boost to go into elliptical orbit to go to geosynchronous. So it could be going with the Earth's rotation to satellite. And Bangladesh put their first one up, and we were doing analysis from the telemetry and the speed and all that. So that was a lot of fun. And there was some physics we had to derive. And we found, this is where it's fun because the community, we found in the military academy, someone had done a nice, tipped me off where something was. And then a Duke professor had a very beautiful trick. So we claimed that our derivation is probably the shortest and best in the world now, because I've checked references. And the Duke guy was humble. He said, I'm not sure if I made up that trick. This is how they review, because this is all generated from the reviewers, and I'm worried about this. So I write back, and I say, look, I have looked on the internet everywhere, and this trick is only found in your Duke notes. So I'm going to give you credit for it. He says, thank you. He says, I must have made up the trick. 15 years ago, he wasn't sure what he got from books and what. So that's fun. You get to interact with the professors, other schools, and all. And with the temperature one, I got to interact with someone at the United States engineering, where they're doing the temperatures, Bureau of Standards and stuff, and they're doing that, and expert on like refraction and like that, and had nice conversations with me over, because what I worried about very much in that Mirage is that everyone was being cavalier with the formula. Some were using red light, some were using laser, maybe yellow, some were, so wait a minute, they got to do all the lights. So I had to do, and this was people very, very sloppy, because they would reference other things and not know what they were referencing. So I says, all right, I'm going to do red light at the end of the spectrum, and I'm going to do blue light, and I got the same angle. So I said, I'm good, all right, because I did not, using some angle in the middle, what's that? I mean, what's going on, see? So little subtleties like that, then you kind of feel like you actually know something that others don't know, because you're really digging the references. I mean, you're getting them from Nancy, whatever, and they're just looking at these things, and you have to like trace them. This reference, this paper, this paper, and you're going back in history. It's like, it's fun, like genealogy stuff, and then put it all together. So when in doubt, reference. Any other questions? All right.
For the speed of the car, did you think about trying to use a cruise control?
I didn't, but I didn't. My wife had a very steady speed, but I think one of the reviewers mentioned that. So I didn't. So that's when we said plus or minus like a mile per hour or something. We're not sure. And then I did something for the reviewer on that. I says, all right, let's say I was 72, but then if I was 68, going to cancel. But let's say I didn't cancel and I stayed 70. Then you found out that 2 out of 70, like 3%, like it's not going to change. So we're within the 3% plus or minus. That's about what we were, So it was like it was okay. But yeah, that would have been nice to. Don't think about these things. Like think of the truth, and think that there's a thermometer gauge in the car. That was the real. I really felt bad about that. Just to get over that.
Probably very timely you did it now, because with self-driving cars coming along,
yes,
won't be able to
yeah.
repeat this maybe.
And that was. I mean, we're going on vacation. That was just total. It just came to my mind. I saw it.
So I think, Dr. Ruiz, it might have been better that you didn't use the temperature of the car, because don't you then get into scrutiny of the accuracy of the thermostat in a piece of equipment.
Yeah, I mean, ideally that's supposed to be giving you the temperature outside because you are moving, air rushes, and there could be a lot of other questions of just how accurate that thing was. That's.
I think you did yourself a service getting professional, external data.
That's true.
Versus, the temperature from a Chrysler, whatever y'all.
Yeah, that's true. Yeah, you don't know how good those things are. Sure, makes me feel better now.
You'd have to get, a calibration certificate from the dealership or something. You don't want to do that. I mean, you want to rely on a professional, licensed expert, I think. And so I think that your approach, although I know it was a challenge for you with the reviewer, I think it served you well.
And I have a similar challenge now with a new paper I'm writing with Brian Hart, who left us for the chancellor, office assistant. He took video of Looking Glass Falls in 14 degrees, like -3 Celsius, like 14 degrees Fahrenheit, and the waterfalls like frozen, and the water's coming down, and it's like freezing right in front of us to a slush ice. Gorgeous. And now I have the temperature at Brevard College, and I treated Chris to lunch the other day, so I could pick his brain. I want the temperature 2,000 feet higher, and the meteorologists have these rules to help that. So we're trying to rely on professionals once again. And then he said, he says you for that day, that winter, in our location, 4 Celsius every 1,000 feet. I could write private communication. He says, well, they'll come after me then. I said, no, they'll be impressed. You're the professional. The physicists will be impressed. They'll respect that. But that's another example. I want to rely on Chris. Although Chris did say, why don't you go down there with a thermometer? I really didn't want to do that at the time and have to wait until it's cold, but he was saying just go down, then drive up and check. But they have this as lapse rate. Like when you go up a certain amount of feet, the temperature, it gets cooler. It's cooler. So, but if I reference him, the expert, I feel comfortable. Yeah, good shape. Yeah. All right. Thank you.